Have you ever wondered what the future of space travel might look like and the role propulsion engines will play in it? Propulsion engines are the heart of any spacecraft, the powerhouse that propels us beyond the confines of our pale blue dot and into the vast expanse of the cosmos. As we stand on the precipice of a new era in space exploration, a multitude of innovative propulsion methods are emerging from the drawing boards and laboratories of scientists around the globe. From the highly efficient ion thrusters and revolutionary nuclear thermal propulsion, to the fuel-less solar sails and the theoretical electromagnetic drives. From the promising nuclear electric propulsion and the speed-focused laser propulsion to the mighty antimatter propulsion and the sun-mimicking fusion propulsion. Each brings its unique strengths and challenges to the table, promising to redefine our journeys through the stars. Join us on this journey as we explore the engines that might propel us into the future. First on our list is ion thrusters, a technology already in use and advancing. Ion thrusters might sound like something ripped straight from a science fiction novel, but they're very real and are already propelling us deeper into space. So what exactly are ion thrusters? To put it simply, these are engines that use electricity to create thrust. How does this work? Well, an ion thruster works by ionizing a neutral gas, typically xenon, to produce ions. These ions are then accelerated by an electric field, creating a stream of charged particles shooting out of the back of the engine. This stream generates the thrust that propels the spacecraft forward. Now, you might be wondering, why ions? Why not just stick with the good old combustion engines we've been using for ages? Here's where things get interesting. Ion thrusters offer a level of efficiency that traditional chemical rockets simply can't match. While chemical rockets burn their fuel in a matter of minutes, ion thrusters can keep going for years. The thrust they produce is much gentler, more like a whisper than a roar, but over time, this whisper can push a spacecraft to incredibly high speeds. Currently, ion thrusters are used in a variety of missions, from maintaining the orbits of communication satellites to propelling deep space probes on their long journeys. The European Space Agency's Smart 1 lunar mission and NASA's Dawn mission to the asteroid belt are just a couple of examples of successful missions powered by ion propulsion. Looking to the future, ion thrusters hold immense promise. Their high efficiency and longevity make them ideal for long-duration, deep space missions. As we continue to refine this technology, we can expect to see ion thrusters playing a crucial role in our exploration of the solar system and beyond. As we venture further into the cosmos, it's clear that we'll need to think beyond traditional rocketry. Ion thrusters, with their high efficiency and longevity, are a promising step towards our future in space. Let's sail into our next propulsion method, solar sails. Imagine a ship sailing across the cosmic sea, tugged along by the gentle push of sunlight. That's the essence of a solar sail, a spacecraft propulsion system that doesn't require any fuel. Solar sails operate on the basis of light pressure. Yes, light has pressure. Even though it doesn't have mass, light has momentum, and when it hits a reflective surface, it imparts a small push. It's like a gentle, continuous breath of wind on a sailboat, but in space. The sails themselves are incredibly thin, often just a few micrometers thick, and can span hundreds of meters. They reflect the sunlight, and the momentum of that reflected light provides the thrust. The pressure is minuscule, but it's continuous, and in the vacuum of space, it can add up over time. The beauty of solar sails is their potential for long-duration, deep space missions. Unlike traditional rockets that burn fuel in powerful but short-lived bursts, solar sails provide a steady and unending push. This means that given enough time, solar sails can reach remarkably high speeds, all without carrying a single drop of fuel. Solar sail technology is not just theoretical. It's been put to the test and has shown promising results. The Japanese spacecraft Icaros, launched in 2010, successfully demonstrated solar sail technology in a mission to Venus. More recently, the LightSail 2, a project by the Planetary Society, has been orbiting Earth propelled only by sunlight since 2019. But solar sails are not without their challenges. Steering a solar sail spacecraft is tricky, as it depends on the orientation of the sail to the sun. Also, the farther from the sun the sail gets, the less effective it becomes. Still, the potential of solar sails is immense. They could be key to future interstellar missions, enabling us to explore the cosmos without the constraint of fuel. Imagine a fleet of spacecraft, their sails gleaming in the sunlight, setting off towards distant stars. Solar sails, harnessing the power of sunlight, present a fuel-less path to the stars. Moving on, we delve into the world of electromagnetic drives. Electromagnetic drives, or EM drives as they are commonly known, are a theoretical propulsion system that have stirred quite the controversy in the scientific community. This is because, in essence, EM drives propose to defy what we understand as the laws of physics. Let's break it down. The proposed working mechanism of an EM drive is to produce thrust without the need for any propellant. How, you might ask? Well, by bouncing microwaves back and forth inside a closed container. The idea is that these microwaves would generate a force on the walls of the container, thus producing thrust. Now, this is where the controversy kicks in. According to Newton's third law of motion, every action has an equal and opposite reaction. But if an EM drive is producing thrust without expelling any propellant, what's the reaction? This apparent contradiction has led to a lot of skepticism about the feasibility of EM drives. However, despite the debates, there are still those who believe in the potential of EM drives and are pushing forward with research. In fact, several experiments have been conducted, with some even claiming to have observed a small amount of thrust. Critics argue that these observations could be due to experimental errors or unaccounted factors, but proponents maintain that there's something worth investigating here. It's important to note that the concept of EM drives is still very much in the realm of theory and speculation. There's a lot we don't know, and a lot of questions that need answering. But that's what makes science exciting, isn't it? The quest for knowledge, the thrill of discovery, the challenge of pushing the boundaries of what we know and understand. So, while EM drives might seem like something out of a science fiction novel, who knows what the future holds? After all, many of the technologies we take for granted today were once thought to be impossible. Despite the debates, EM drive remains an intriguing concept in spacecraft propulsion. Next, we explore the combination of nuclear and electric power in nuclear-electric propulsion. Imagine a spacecraft engine that marries the best of both worlds, nuclear energy's immense power and the efficiency of electric propulsion. This is precisely what nuclear-electric propulsion, or NEP, brings to the table. In an NEP system, a nuclear reactor is at the heart of the operation, but instead of directly expelling heated propellant to generate thrust as in nuclear thermal propulsion, the reactor here generates electricity. This electricity then powers an electric propulsion system, often an ion engine, to accelerate ions and create thrust. Now you might be wondering, why go through the extra step of converting nuclear energy to electricity? Well, the answer lies in the very nature of space travel. It's not just about raw power, it's also about efficiency and sustainability. The addition of an electric propulsion system allows the spacecraft to use fuel more efficiently, providing a longer operational life and making deep space missions more feasible. One of the biggest strengths of NEP is its potential for scalability. It's a system that can be scaled up or down, making it suitable for a range of missions, from sending small probes to distant planets to potentially powering human missions to Mars and beyond. However, like most advanced propulsion concepts, NEP has its challenges. The technology to safely and effectively convert nuclear energy to electricity in space is still being developed. Yet, the potential benefits offered by NEP make it an exciting area of research in the quest for the next generation of spacecraft propulsion. In essence, nuclear-electric propulsion could be a game-changer. It's about balance, a balance between the raw power provided by nuclear energy and the efficiency of electric propulsion. If we can master this technology, it could open up new possibilities for deep space exploration, from visiting distant planets to setting up human colonies on other worlds. NEP could be the key to achieving a balance between thrust and efficiency in space travel. Now let's shine a light on laser propulsion. Imagine this, a spacecraft soaring through the cosmos, propelled by beams of light. Sounds like science fiction, right? Well, this is the concept behind laser propulsion, an idea that could revolutionize space travel and enable mind-boggling speeds. Laser propulsion involves using ground-based lasers to propel a spacecraft. Picture a powerful laser beam shooting up from Earth, hitting a spacecraft, and causing it to move. But how does this work? It's all about momentum. When the laser hits the spacecraft, it imparts momentum to it, pushing it forward. The beauty of laser propulsion lies in its potential for high-speed space travel. With chemical rockets, we're limited by the speed of the expelled gases, but with lasers, there's no such limit. In theory, a spacecraft could reach a significant fraction of the speed of light, making even interstellar travel a possibility. The propellant for this system? Light itself. That's right, light. No need for heavy, cumbersome fuel tanks. No more worrying about running out of fuel in the middle of nowhere. This could make space travel a lot more efficient and economical. Of course, there are challenges. For one, we need extremely powerful lasers, much more powerful than anything we currently have. Then there's the question of aiming. The laser needs to hit the spacecraft precisely, even when it's thousands or even millions of miles away. And of course, there's the issue of energy. Such a system would require enormous amounts of power. But despite these challenges, research is ongoing. Scientists and engineers around the world are working on this concept, trying to make it a reality. And who knows? Maybe one day we'll see spacecraft zipping around the cosmos, propelled by beams of light. Though still conceptual, laser propulsion could redefine our approach to space travel. Moving forward, we delve into the exciting world of antimatter propulsion. Imagine a propulsion system that could propel a spacecraft with such efficiency that interstellar travel becomes not just a possibility, but a reality. That's the potential of antimatter propulsion. Antimatter is the mirror image of normal matter. For every particle of matter, there's an equivalent particle of antimatter with the same mass but opposite charge. The magic happens when matter and antimatter meet. They annihilate each other, converting their mass directly into energy. This is governed by Einstein's famous equation E equals mc squared, which tells us that a small amount of mass can be turned into a large amount of energy. This energy release is vastly greater than what we see in nuclear reactions, making antimatter an incredibly efficient fuel source. If we could harness it, just a few grams of antimatter could propel a spacecraft to a significant fraction of the speed of light, drastically reducing travel times to distant stars. However, the catch is that antimatter is extremely difficult to produce and store. Even with our most advanced technology, we can only generate tiny amounts of antimatter, and storing it is even more challenging. Antimatter reacts explosively with regular matter, so we need to keep it isolated in a vacuum, using magnetic fields. Moreover, there are safety concerns to consider. An antimatter reaction is potentially explosive and needs to be carefully controlled. Additionally, the annihilation process produces high-energy gamma rays, which present a radiation hazard. Despite these challenges, the potential benefits of antimatter propulsion are so great that research continues. Scientists are exploring methods to generate, store, and use antimatter more efficiently. They're also investigating ways to manage the risks associated with its use. Antimatter propulsion, while still largely theoretical, holds incredible promise for the future of space travel. As we continue to push the boundaries of technology, who knows what possibilities may unfold. With antimatter propulsion, we might one day be able to reach the stars, opening a new chapter in our exploration of the universe. Lastly, we touch upon the power of the sun with fusion propulsion. Fusion propulsion, as the name suggests, is a concept that aims to harness the titanic energy of nuclear fusion, the same process that fuels our sun and other stars in the universe. Imagine having a miniature sun powering your spacecraft. The idea revolves around combining light atomic nuclei at high temperatures to form heavier nuclei. This process, known as fusion, releases a phenomenal amount of energy. It's this energy that fusion propulsion seeks to use, converting it into a high-speed stream of particles to push a spacecraft forward. Now you might be wondering, why fusion? What makes it so special? Well, the answer lies in the sheer efficiency and power it promises. Fusion reactions have the potential to produce many times more energy than traditional chemical reactions. This means a spacecraft with fusion propulsion could achieve much higher speeds, reducing the time it takes to travel vast interstellar distances. However, as exciting as it sounds, fusion propulsion is still in the early stages of research. Scientists and engineers are grappling with several challenges, such as how to contain and control the fusion reaction, and how to convert the energy produced into useful thrust. But despite these challenges, the promise of fusion propulsion is too great to ignore. The technology could revolutionize space travel, making long-distance interstellar journeys not just possible, but practical. Picture this: missions to far-flung planets and galaxies, powered by the same energy that lights up the stars. It's a thrilling prospect. To sum up, fusion propulsion represents the pinnacle of what might be achievable in spacecraft propulsion. It's a concept that combines the power of the stars with our desire to explore the cosmos. Harnessing nuclear fusion, fusion propulsion could be the key to our future in space. As we reach the end of our journey, we can see that the future of space travel is bright and full of possibilities. The engines we've explored today, each with its unique strengths, are all pushing the boundaries of what we once thought possible. From the efficiency of ion thrusters and the high thrust of nuclear thermal propulsion, to the fuel-less journey offered by solar sails, There are so many routes to traverse the cosmos. The controversial but intriguing electromagnetic drives, the balanced approach of nuclear electric propulsion and the high-speed potential of laser propulsion all paint a fascinating picture of our journey to the stars. The theoretical yet immensely powerful antimatter propulsion and the sun-mimicking fusion propulsion promise a future where distance is no longer a barrier to exploration. While we may not know exactly what the future holds, one thing is certain: the journey to the stars will be powered by some incredible engines.